This is the O2 superstructure. We've got a hull length here of just over 72 meters, which is actually about the same size as a 747 jumbo jet. The reason that we need such a big hull is that we're generating a lot of power, so we need to actually have buoyancy to counteract the load that is coming from the rotors. So each rotor is imparting about the same thrust as a jumbo jet's engine's taking off.
A global industrial revolution is underway.
Yes, we have a technological challenge for our environment, for the well-being of the population of the planet, for civilization.
Driven by passionate, dedicated individuals intent on shaping a new world.
I do it because I look at my kids, and I honestly am convinced that this is the way.
A cleaner world.
There is a way forward other than burning fossil fuels out of our funnels.
A greener world.
This wind farm is producing more hours of power into the grid than all wind farms in the UK and probably in the world.
What we've done in the past is not going to solve these challenges. We need to find new ways, and I think the only way to do that is to bravely step forward and implement technology.
Together, they are pushing engineering to its limits to create extraordinary machines that can protect our planet for the future. Anyone who has spent time by the coast will have witnessed the raw power of the ocean. As tides rise and fall twice a day, vast amounts of water swirl around the Earth. This is a huge energy source that's currently largely untapped.
500 million tons of seawater an hour go through these gaps. Those are titanic forces.
An estimated 3,000 gigawatts are available to be harvested globally, enough to power a third of the Earth's homes. Yet compared to wind and solar, the technology needed to harness tidal power is still in its infancy, and the challenges of operating in these environments are enormous.
The ocean can be cruel at the best of times. And then you'd move that water at 10 knots, which is like a 100-knot wind. So you can imagine that's a very, very, very aggressive environment for these machines to survive in.
Yet there are teams of engineers around the world determined to take on that challenge, to help the planet. Their goal is to build machines that are tough enough to not only survive these conditions, but thrive in them.
The wind's been harnessed, solar's been harnessed. We're trying to bring a new industry to the world.
Although these turbines are destined to be submerged below the sea, the vast energy they're designed to harness owes its existence to a phenomenon high above our heads: the movement of celestial bodies through space. The moon is closer to the Earth's surface than it is to the center of the planet. That means its gravity pulls slightly harder on the ocean nearest to it than on the rest of the Earth, creating a bulge of water. The moon's gravity also acts more strongly on the center of the Earth than on the furthest ocean, creating another bulge. These two swells of water appear as high tides at the coast. As the Earth spins, both of them move around the planet's surface, so that most places experience 2 high tides a day and 2 low tides. Twice a month, when the Earth, Moon, and Sun align, their gravity is combined, and you get even bigger tides, called spring tides. The rise and fall of the Earth's seas and oceans represents a vast amount of energy. People have harnessed that power since time immemorial. And a handful of tide mills still make flour today.
A tide mill has been here for 850 years. Grain would be grown here, collated at this mill, and then processed, and then it could be easily shipped away.
Dan Tarrant-Willis knows the rhythm of the tides as well as anyone.
The tide affects my life in a beautiful way because I kind of live by the tide. So I know I'm working if it's low tide. If it's not low tide, I'm not.
Behind the building is a mill pond. When the tide comes in and the water level rises, the pond fills.
It has a one-way valve in it, so as the water rises, it fills the mill pond. That fills up to the height of the tide. We then wait until low tide, and at low tide, we empty the water that we've captured at high tide underneath our wheel.
The wheel is connected to a shaft, which turns a set of millstones.
That turns at about 50 RPM, which is perfect for turning wheat into flour. There are 2 low tides in each 24-hour period. I've basically only got 2 hours a day that I can mill.
During the Industrial Revolution, tide power gave way to coal-driven steam power, which was available on demand. After that, tidal technology almost disappeared, with a notable exception. In 1966, a tidal barrage was built across the mouth of the Laurence River in France that still operates today. As the tide rises and falls, water pours through 24 turbines, generating enough electricity to power the nearby city of Rennes. But the structure was very expensive to build, and it damaged the estuary's ecosystem. Interest in tidal energy reached a low ebb. Yet recently, engineers are starting to look to the ocean again. The climate crisis has given fresh impetus to finding clean energy sources to replace coal and gas-fired power stations. And tidal energy has a crucial advantage over wind and solar power.
The greatest thing about the ocean is its dependability. We know that the tide comes in and out. We have tidal charts going back hundreds of years. That's always going to be that set amount of energy, that time of day, the tide, and we can rely on that. That's the biggest upside of what we try to do with marine energy.
Drew Blaxland of CIMEC Atlantis has been working for decades towards a new way to capture the tide's power. Now it's being put to the test. June 2016, the AR 1500 tidal turbine is being assembled at a research center in northern England.
This is a very exciting moment for myself and everyone in the team. This is the world's first commercially viable tidal turbine for the world's largest tidal energy array in the world.
It's designed to generate power in the open ocean. The machine looks like a wind turbine that sits on the seabed, 100 feet below the surface. It's driven by tidal currents. These are created by water flowing towards parts of the sea where the tide is rising. When the tide changes, the turbine rotates to catch the flow in the other direction. The current drives the rotor around, turning a shaft which goes inside a waterproof casing called a nacelle. There, a generator produces electricity, which flows back to shore through an undersea cable, where it connects to the grid. Each unit is designed to generate enough electricity to power 650 homes, day in, day out. It's much simpler and cheaper to build than a tidal barrage, and should have less impact on the environment.
The greatest thing about what we do is the turbines turn up off the back of a ship, lots of activity, this beautiful, pristine environment, and after we leave, it's still a beautiful, pristine environment. You don't know we're there, and there's now power being generated.
But before disappearing beneath the waves, the turbine must first prove itself on land, without its blades. The team connect the shaft to a test rig to simulate the extreme dynamic loads it will experience under the sea. Over the course of 6 weeks, the powerful test rig drives the shaft with the same force as it will experience under the full tidal flow. But as well as turning the shaft around, the test rig can apply hundreds of tons of force, pushing it back and bending it to the side, just like the turbulent ocean. Despite the punishing loads, the powertrain, bearings, and control systems all work perfectly.
It's an absolutely huge milestone for us, and the feeling is absolutely excellent. It's the kind of thing that you spend your whole career building up for, is these moments when you can say that all that hard work was really worth it.
The turbine's ultimate destination lies off the northern coast of Scotland, where the tides are legendary. Orkney, a remote windswept archipelago. The raw power of the ocean around the islands is breathtaking. For 15 years, Neil Commode has run a marine test site for wave and tidal energy devices here.
There's a huge amount of tidal energy in the waters just around Orkney. It's estimated it's something like 20% of Europe's tidal energy are here in the waters around these islands.
Traveling around the islands can take much longer at certain times of day than others, depending on which direction you're heading.
Well, it appears that we're powering along at a brisk 8 knots or about 10 miles an hour. But actually, if you look at the side, you can see we're not moving at all because the boat is having to work against the tide.
Although the vessel is moving rapidly through the water itself is flowing at roughly the same speed in the opposite direction. Despite its appearance, the water is moving faster than most whitewater rapids. The reason the flow here is so fast is because of Orkney's unique position.
Orkney has got 2 bodies of water around it. It's got the North Atlantic and it's got the North Sea. And the North Sea at the moment is higher than the North Atlantic. So the water is running downhill towards the North Atlantic. And 6 hours later, it all turns around and goes back the other way again.
As the water pours from one sea to the other, it's forced into narrow channels between the islands, making it speed up even more. When the tide changes, the currents slow down and stop before starting to flow back.
500 million tons of seawater an hour go through these gaps. Those are titanic forces.
These powerful currents are known as tidal streams, and they're a huge potential source of clean power.
We're standing effectively on a river of energy that's roaring past us, that's driven by the position of the moon and the sun, and that's never ending. So if we can tap into the currents and the energy that's in this water, that gives us, frankly, an inexhaustible power supply.
Experts estimate tidal streams in places like Orkney could one day meet 1/5 of the world's electricity demands. The stretch of water with the most potential here is the channel between the islands and mainland Scotland, the Pentland Firth. Here, the water flows so fast, it's been called the Saudi Arabia of tidal stream energy. There's enough power to generate a vast 4.2 gigawatts of electricity, more than the world's biggest wind farm and solar farm combined.
The flow in the Pentland Firth is fantastic for tidal turbines. You have the North Sea and the North Atlantic, and the tidal exchange between the two, you get tides up to 10, 11 miles per hour, which is great for tidal generation. It's 100, 120 feet deep, 30, 40 metres. You really couldn't ask for a better place to do tidal, and reasonably close to shore as well.
CIMIC Atlantis will deploy 4 turbines here at first, with plans to scale it up to an array of hundreds of machines in the future. The first AR-1500 turbine has arrived, and its 3 30-foot-long blades are assembled into the rotor, spanning an area the size of a tennis court.
The bigger your rotor is, the more power you're able to generate, the more yield you can take for any given megawatt.
With the blades on, the machine stands 78 feet tall.
It's 4 to 5 stories high, it's 150 tonne plus the foundation, it's 1,300 tonne of steel. It's a big beast.
The huge structure must be transferred to a ship to sail out into the Pentland Firth, one of the world's most challenging locations.
The tide is roaring along for most of the day, a good 20 out of 24 hours, up to 10 miles an hour, depending on the site. And you've got to get in there in the 4 1-hour maximum hour periods to do your work. So you've got to find ways of designing your equipment and everything you do for that little tiny period of time. It's almost military precision. You need to go into it almost like you're planning a battle, and you go out, jump out of your trench, do your thing, and then scurry back in your trench for the next 4 hours and have another crack.
A high-precision operation like this needs a sophisticated dynamic positioning vessel. It uses satellite technology to remain stationary despite the currents. But the water here flows so fast that the operation must still be completed in the short window of slack tide, when the current slows down before it changes direction.
So what we've actually done is we've installed cameras in the bottom of our turbine. You've also got an ROV, a remote operated vehicle, which is a robot effectively that can watch the turbine as it comes down. Imagine that is the top of a foundation. Big pole, 2.5 metres diameter, sticking out of the seabed, and you're aiming for that. And that's the female connection. At the bottom of the turbine, this is now coming down from the top, is the male connection.
The tide has now turned, and the water's starting to flow. It's already pushing the turbine out of line. In a few minutes, the current will be too fast for the vessel. But if they abort, it means a 6-hour delay.
Time is money. Every day we're offshore with large vessel assets costing, $50,000 a day plus. So time is absolute critical offshore.
The team have one last chance to make the connection.
The next trick is you don't even have to get it that close. You have to get it within tolerance, and we have special features on our stabbing system that allow it to turn on its own as it comes together. And that's basically like a bayonet fitting that brings it together. Once it's together, that's it. There is no extra fasting, there's no clamps. It's 150 tonnes, about 90 tonne underwater, because you lose weight as you go in the water, and it sits there just on gravity.
3 more turbines are also taken out and installed in the Pentland Firth. A project called Maygen that can power 2,600 homes with green electricity.
So at the Maygen site, we have 4 1.5 megawatt turbines. That's reasonably small in comparison to wind, but it's the start of tidal arrays.
As well as installing the turbines quickly, the same system can also be used to retrieve them for maintenance. But they still need expensive equipment to do it. So if the turbines need many repairs, the mounting costs could be prohibitive. On the west coast of Scotland, a different tidal device is being developed to avoid that risk. Connell, on the shores of Loch Etive. During spring tides, conditions here draw kayakers from around the world to brave the famous tidal race called the Falls of Laura. Evidence of the plentiful tidal energy available.
The water flows up into Loch Etive, and then it comes out in a great rush past the Falls of Laura. And it's almost like a horizontal waterfall where it really rushes through there at a huge rate of knots.
Jason Heyman is CEO of Sustainable Marine Energy, another tidal stream startup based in Scotland. His vision has been influenced by seabed-mounted turbines he's worked with before.
We were installing a first-generation device on the seabed. And so we looked at that and we said, that's great, we can see the potential for this, but it has to be far simpler and far more cost-effective. And that's when I decided to look at other ideas, and that's why we started Sustainable Marine.
In 2017, Jason's team assembled a new device to harness the power of tidal flows at the Falls of Laura. But he decided to try a different approach. His plan was to build and test a floating platform with tidal turbines that can be lowered beneath it.
We thought by having a floating platform, then we can make it more like a conventional ship. And we can take a little boat and we can go there whenever we want. And if we need to change a fuse, if we need to try a new blade, if we need to try anything new, we can do it, and it's easy.
The platform is held in place by mooring lines, while 4 relatively small rotors are lowered down into the water. As the tidal stream flows past, the turbines generate 280 kilowatts of power. When the tide turns, the platform is carried around by the current, so it can produce electricity on the rising and falling tides.
We are producing electric current with the turbines submerged under the water, and this is then transferred to the container for power conversion and then be fed into the grid. This is the next generation of tidal power.
Unlike seabed-mounted turbines, floating platforms are not hidden from view beneath the waves, so they do have an impact on the landscape. But being at the surface does have other benefits.
The water flows faster at the surface because at the bottom of the ocean you have the seabed, and the water moving along next to the seabed encounters friction. It has to get past all the crevices and rocks and everything. Therefore, you want the turbines positioned as high in the water column as you can get them to get the maximum amount of energy out of the water column.
With a faster flow of water, even small rotors can generate powerful forces. So the team need to check whether the mooring lines can hold firm.
The thrust force that's generated by one of our turbines is the same as a Eurofighter Typhoon when it's on full afterburner. So if you imagine with our platform, that's like saying, let's take a brace of Eurofighters and try and put them on a leash and then hit the afterburners. So that's how big the challenge is.
The trial in Scotland has proved that the mooring lines and platform can withstand the colossal forces and generate electricity reliably. But to be used more widely, the team also need to check how their technology affects wildlife.
It's all very well going and deploying something into the natural environment and saying, hey, this is going to help us avoid greenhouse gas emissions. But what impact is it going to have on the local environment? And we need to understand that to ensure that we don't create a situation where we create unintended consequences.
Researchers are monitoring the behavior of marine animals around the platform and investigating what effect the turbines could have.
Tidal turbines are mechanical structures. They make noise. There's often concerns about the amount of noise they make, that it's too much, that it pollutes the environment. However, we've got other concerns about tidal turbines, that they might be a risk for marine mammals and other large animals swimming around in the water column, and the risk is that they might bump into the turbines. So it's important that the noise that the turbines are making is loud enough for the animals to hear it at a distance that's far enough away for them to move away, but not so far that they avoid the whole area where the turbines are and the environment they're going through. So there's a kind of sweet spot between being too loud and causing disturbance and being too quiet and them having a collision risk.
So we've had seals and porpoises and even whales come past the platform, and we've had no signs of any interaction, and they just seem to cruise on by. The seals actually seem to like to play behind the platform somewhat in the wake. And now what we're really trying to understand is how fish interact around the platform and how they avoid the turbines.
After successful test campaigns, the team intended to scale up the device. As head of research and development, Penny Jeffcoat worked with the engineering team to create the new blueprint.
One of the things that we learned from having a 4-turbine platform was that the platform and the mooring system cope perfectly fine with all of the thrust and other loads that we were putting through the system. So it meant that we felt confident that we could design something that could accommodate more turbines and more power and more thrust and more load.
Before building the new larger platform at full scale, they had to be sure the design could withstand the extreme conditions it would face. The Flowwave testing tank in Edinburgh, Scotland is the only place in the world that can reproduce any sea state. With a circular shape, it can create every possible combination of waves, currents, and depth.
This means that we can completely accurately replicate what we would have in a real site, but at tank conditions. So it means that we can have flow coming in one direction, waves coming in another direction, and test this at different depths to see how these different phenomena interact.
In 2018, Penny's team built a scale model of the new design. The 6-rotor platform is destined for the Bay of Fundy in Canada, a location with notorious conditions.
It has the highest tidal range in the world, so you've got a 16-metre tidal range. So the flow speeds that we experience at site are between 5 and 6 metres per second. So for the mariners out there, that's more like 10 to 12 knots. So incredibly fast moving water.
As well as dealing with the rapid flow and constantly changing water depth, the platform must be ready for the worst weather that nature could throw at it.
We try and capture as many different combined conditions between flow and waves that we can do, and this might be quite benign. And then we also try to do right up to the extremes. So imagining a big storm coming through, a big hurricane coming through, massive waves coming through the site, how does the platform cope when it's confronted with these monster waves coming through?
As the tank test began, the paddles created miniature versions of storm waves. Underwater, pumps began driving the flow rapidly across the tank.
There is a certain feeling when you're in the tank and you hear all of the pumps like ramping up. And it's brilliant because it just builds up that sense of excitement and anticipation in you. When we're trying to replicate the Bay of Fundy, where we have these really extreme tides, it's actually pushing the tank right up to the extremes of what it can cope with as well.
But as the pumps reached full speed, something was not right.
Sometimes things don't go quite as you're expecting, and this happened quite unexpectedly, that we had a mooring line suddenly break on us as we were operating at the fastest flow.
The team rushed to find out what went wrong, and the answer was soon clear.
It was not through engineering or design, it was completely through me putting the models together slightly wrong, so I apologise for that to the team. But it was a really interesting thing to learn from because we saw exactly, well, what happened to the platform? Where did it go? How did it move in the tank? And actually, even though we lost one mooring line, the platform worked perfectly fine, it coped.
Once the mooring line was fixed, the waves and currents were ramped up again. And this time, everything went to plan.
We were throwing the fastest flow, the highest waves, and it was just performing exactly as we expected. So it was a real sense of such relief and excitement and just real proud of our engineering team for having designed such a brilliant product that did exactly what we were expecting it to do and did exactly how the numerical models predicted. And we had great confidence that yes, we can build this, we can put it in the sea, and it's going to do exactly what we need it to do.
On the east coast of Canada, the Bay of Fundy in Nova Scotia is the ultimate tidal testing ground. The full-size platform is being assembled on the banks. On the 1st of February 2021, it's finally ready to be launched. All they need now is for the tide to come in and raise the water level high enough.
Behind me you can see Plate Ice 640, our tidal platform. And in a few hours it's going to be traveling down this slip. It'll achieve high tide in about 1 o'clock today. We have beautiful wind conditions today, very low wind. So very, very exciting day. This is a culmination of many years of research and development, and can't wait to see our platform in the water.
At high tide, the platform is maneuvered down the slipway and into the bay. It will be moored in a passage with one of the fastest flowing tidal streams in the world. At full flood, 4 times more water moves through the Bay of Fundy than all the world's rivers combined.
Because it's so much energy, it's a very, very challenging site. It's the Mount Everest of tidal sites. And there have been some attempts to deploy technology there before, but unfortunately, nothing's actually managed to work for a prolonged period of time.
If it survives the ultimate test, this still relatively small platform could one day provide electricity to remote islands and coastal communities. But another company back in Scotland think bigger is better. At a construction yard in Dundee, the world's biggest tidal turbine is taking shape. The Orbital O2. Making larger turbines means you need fewer of them to generate the same amount of power. That means fewer cables, anchors, and mooring lines. And less infrastructure means cheaper electricity. But CEO Andrew Scott knows that building bigger also has its challenges.
So this is the O2 superstructure. We've got a hull length here of just over 72 meters, which is actually about the same size as a 747 jumbo jet. The reason that we need such a big hull is that we're generating a lot of power. So we need to actually have buoyancy to counteract the load that is coming from the rotors. So each rotor is imparting about the same thrust as a jumbo jet's engines taking off.
Each of 2 rotors on the O2 will be 65 feet across. Together, they trace out a total area bigger than a basketball court. As the rotors turn, as well as generating electricity, they'll create a powerful torque pushing the front of the machine underwater. The buoyancy of a long tube full of air counteracts the turning force, keeping the nose above water. But in doing so, it causes the structure to flex in the middle.
The rotors exert tremendous forces on the hull, and the hull has to react all this force, and during this process, the hull bends like a banana.
Engineer William Annell has responsibility for the turbine's superstructure. He knows they need to reduce the bending motion as much as possible.
So you can see here that we have to use very large pins, really thick bits of steel in order to resist the forces that are being exerted on the structure. Now, the reason that we do this is to bring the stress levels right down. Some of the bits of plate that we have here are around about 70 millimeters thick. Even the hull has shell thickness of up to 40 millimeters thick in places. Now, if you compare this to a commercial vessel or a military vessel like an aircraft carrier, you'll find shell thicknesses around 8 millimeters.
When the hull was being fabricated, shaping and welding such thick pieces of metal into precise tubes was extremely demanding.
The hull structure has to be manufactured with a lot of precision. In order to resist the forces of the tide, it has to have good uniform shape. The tolerances that we're working to are around about 2 millimeters over 3.8 meters. So that's really high precision stuff. This takes a lot of experience because there's so many factors involved. It's a bit of a dark art.
The design of the O2 owes much to Orbital's previous turbine, the SR2000.
The SR2000 was a tremendous machine. It was a 2 megawatt tidal turbine, 2 rotors extracting energy from the tide, weighed about 505 tons. It was absolutely enormous.
Like the O2, it has a long superstructure with 2 legs to hold the nacelles and rotors underwater. In 2016, the SR2000 was unveiled at the Harland and Wolff shipyard in Belfast, Northern Ireland. Before launch, the team ceremonially blessed the vessel with mugs of local scotch.
It was a lot more effort making the SR2000 than what we'd anticipated. A lot of 12, 15-hour days. So it took a lot out of us. And for me personally, when the machine was launched, there was a sense of relief, and then there was a quiet sense of satisfaction for everything that we'd achieved. When it was launched, it was the largest tidal turbine in the world.
The floating SR2000 was towed north to Orkney, where it was moored in one of the world's fastest flowing tidal streams. Over the course of a 2-year-long trial, the turbine survived waves over 4 meters high and broke the record for the most tidal energy generated by a single turbine, 3 gigawatt hours in its first year alone. This provided the 20,000 inhabitants of the islands with up to a quarter of their electricity.
We made a lot of world records. We made a lot of world firsts as well. We had a very successful testing period generating significant amounts of energy from a tidal turbine, and that hadn't been done before.
But although the SR2000 performed well, the team soon became aware of a major drawback. The 2 legs holding the rotors were designed to tuck up underneath the body, making it easier to tow to harbor. But that meant the rotors and nacelles would always be below the surface, and therefore hard to reach.
It was flawed. By having the nacelles always under the water for the SR2000 meant that inevitably, either through needing to access for servicing or repair, we were going to be faced with the question of having to get access. And that would have to be done either by lifting the entire turbine out of the water or put it into a dry dock. Both those scenarios require a lot of downtime and a lot of cost.
The team couldn't afford to take that risk again. Even something like a blown fuse could take the turbine out of action for weeks. Andrew was determined to find a way to make all the vital components on their next turbine more accessible.
We knew that we had a challenge around low-cost maintenance and servicing of the entire turbine, including the nacelles. So that was something that we put as a priority for the redesign of the O2.
One approach would be to change the position of the legs so the blades and the nacelles could be lifted all the way to the surface rather than being tucked up underneath the hull. But that would mean the turbine could no longer be put in a compact configuration that could easily be towed and docked. Then Andrew realized that if the nacelles and rotors were accessible in situ, that wouldn't matter, as it would never need to be taken to harbor for repairs.
It gave us a bit of an hallelujah moment in terms of how we operate these turbines. And what that really allows us to do is make sure that the turbine spends most of its life generating power, which is what it's meant to do.
In July 2020, the mechanism for the O2 legs was tested for the first time. Lifting them right up to the surface requires new, more powerful hydraulics. The untested technology must now prove that it works.
Today we're just testing the hydraulic retraction system. It's a huge amount of weight, 100+ tons that it has to lift up to the surface. So it takes a huge amount of power to do that, 75 kilowatts of hydraulic power just to lift the legs.
The upper parts of the legs have been attached to the body, ready to test the mechanism. All that's left is to lower them down to their working position and then try to lift them back up.
We don't like excitement. We tend to want the testing to be well planned. I like a boring test. Okay, I'm going to take the legs down.
The legs are fully deployed with no surprises. Next comes the 100-ton lift. On the water, this will raise all the vital components up to the surface, where they can be easily accessed. success. By January 2021, the nacelles are ready to be attached to the legs. Inside are many of the vital mechanical components, including the gearbox, generator, and pitch control units. The final components are the rotors. Although tidal blades operate along the same principles as those on wind turbines, working underwater makes a huge difference.
As a comparison, this wind turbine has a power output of about 11 kilowatts and blade length of about 6 meters. So to do the same with the tidal flow, we'd only need blades of about half a meter in length. The difference is due to the density of water. Seawater is more than 800 times denser than air. The energy density in the tidal stream allows us to generate a lot more power for a given swept area.
Finley Wallace is the lead blade designer at Orbital. The blades he's creating for the O2 will be roughly twice the length of this small wind turbines, but should capture 100 times more power. The rotors are being made in Gosport, England. The team are using layers of carbon fiber, a material that once treated will have the right strength and stiffness to reinforce the structural core of the blades.
The forces involved in acting on a tidal blade are orders of magnitude higher than an equivalent wind turbine blade. So standing up to the marine environment is the real difference for me.
To form the core of the blades, the carbon fiber must be infused with resin and then heated.
We're actually standing inside an oven at the moment, looking at the main structure of the O2 2000 blades. There'll be 4 of these produced, 2 for each rotor set, and they'll do the majority of the work of transmitting the blade loads from the tidal flow into the turbine structure.
While the core of the blade should be strong, the exterior must be perfectly shaped to interact with water and generate power.
I spent a lot of time fine-tuning the external shape of the blade to present the smoothest path for the water to flow over. The water flowing past the blades is what allows us to generate electricity from the water itself.
The computer-controlled cutter can exactly recreate the hydrodynamic curves of Finley's digital design. But the automated process leaves unwanted ridges on the surface. These are smoothed out by hand to produce a perfectly polished edge.
Being able to kind of stand in front of the molds and see that it's kind of gone to plan, as far as that's concerned, has been very rewarding.
In February 2021, the blades arrive in Dundee, ready to be painted and attached. Once in place, Orbital will test the giant turbine back in Orkney. When they connect to the grid, it should generate more power than any other tidal stream turbine. After that, they have big plans.
The long-term goal is to produce lots of machines so that we can have farms of tidal turbines in various sites around the UK and around the world.
In the future, arrays of tidal stream turbines could generate huge amounts of power for local communities and national grids. Yet despite the clear promise of the technology, some experts question whether tidal stream power could ever become as widespread as wind or solar. Surveys suggest the number of places with fast enough currents is limited. In the vast majority of coastal locations, the water simply doesn't flow fast enough for seabed-mounted or floating turbines. However, a company on the west coast of Sweden is trying an approach that could work in more places, with a design that's fundamentally different from other tidal stream turbines. Rather than being fixed in place, this turbine is designed to move. CEO Martin Edlund believes this is the secret to extracting more power from slower currents.
The Minesto technology is unique compared to hundreds of other tidal solutions that exist today. So what we do is that we basically fly an airplane underwater tethered to the seabed. This technology can be used in all continents and all oceans around the globe, and that's a huge advantage.
The Deep Green 100 prototype has wings like a plane, but it moves more like an underwater kite. On a day with slow winds, there's a trick that allows you to still fly a kite.
The wind speeds today is really near to nothing, about 1-2 meters per second. But flying the kite in a figure eight allows us to get more energy out of it.
When there's not much wind, a stationary kite can't stay aloft as there's not enough power in the air to lift it. The only way to fly a kite in these conditions is to keep it constantly moving, faster than the wind itself. That way, it collects and combines the power of the wind over a much larger area, keeping it in the air.
Our turbine is like a normal kite, but instead of powered by wind, it's powered by water. That's exactly how a kite behaves underwater in this figure eight behavior.
Minesto's subsea kite is designed to be tethered to the sea floor and to move continuously through the water in a figure of eight, flying much faster than the water is flowing itself. The rotor on the front is pushed round, generating electricity, which flows down the tether and back to shore. By harvesting the power of the flowing water over a large area, it can extract many times more power than if it were fixed in place, like other turbines. At the workshop, the gearbox, generator, and the rudder module are being tested. The team are checking that the systems are correctly calibrated so it can maneuver reliably underwater.
We're doing some fine-tuning of the most important section of the kite that actually doing the work, which is the rudder module, rudder and elevator module. So we have the rudder here that controls the steering of the kite, and then we have the elevators, which is basically the throttle.
The rudder module is entirely responsible for the kite's trajectory underwater. If it doesn't move as intended, the kite could crash into the seafloor or tie itself up in knots.
Maybe 1 degree of difference has a huge impact on the performance of the system. So we really need to nail this so we get the most out of the system.
The rudder and elevators are connected to an onboard control module. Once the team have chosen how they want the kite to behave, it flies automatically.
It's what we call the kite control module. That's where the magic happens. We create system code, clearly, and then we program it into this control unit. And then we just tell the kite to run. And it will then automatically adjust its actuators within given parameters that we've set. It could be kite speed, depth, and so forth. And within those boundaries, the kite's making its own decisions and is really good at it.
To make the right decisions, the kite has a gyro unit and sensors. These tell the control module what depth, speed, and orientation it has at all times, so that it can respond appropriately. The team need to check all the sensors are working as intended.
If you imagine you have your smartphone, where you can flip the screen and you can like roll balls in games and those kind of, it's more or less the same thing. We set the kite into motion and we can see that the rudder module reacts the way we want it to. So we're happy.
Minesto have been testing underwater kites for 10 years around the coasts of Northern Ireland and Wales. During that time, they've developed their seabed tethering technology and devised the most efficient systems for transporting the power back to shore. All this while improving the technology that flies their kites through the water, leading to the development of the high-performance DG100.
We needed the robust systems to fine-tune and work with control system, get all the functionality in place. But what we're doing now is that we're aiming higher and we're moving towards real performance output of what we're doing. And I think it's fair to say that this version we have now is more of a Formula One car than a robust, safe Volvo that we've been working with before.
Minesto chose the Faroe Islands in the North Atlantic to trial the DG100. Here, the tidal currents are much slower than in Orkney or Canada. But Monesto calculated they could still supply 100 kilowatts of electricity to the grid, enough to continuously power over 1,000 TVs.
The flows in most locations are not high enough for what we may label conventional tidal turbines. For us, this campaign is the key campaign to really prove the high-performing energy conversion that we're claiming, which makes it then sort of the absolute most important testing campaign that we've had in Monesto.
First, the team had to build the infrastructure to fix the kite to the seafloor and bring the power onshore. Once that was in place, the kite was towed out to sea. But during tow testing, the team realized that there was a problem with the electrical connection. The system had detected a leak, which had to be fixed.
You can imagine, I mean, we're all excited about this control system team in place. Everyone really wants to see this thing flying. And then there is a minor, insignificant part of a component that's... Again in this. That's sort of the nature of pushing the boundaries of technology and driving innovation.
After 3 weeks and a lot of late nights, the kite was back in the water.
Towards the end of November, we had really good tidal conditions, good weather conditions, and we said that it's about time now to get everything right and hook this machine up to the grid and fly it. And we knew that we were very, very close to success.
The tether was attached to the seafloor, and in the control room, everything was finally ready. The team were raring to go. The kite sank deep into the murky depths and out of sight. Finally, the test could begin.
We started running it in continuous operations mode with some safety belts on, not letting it loose completely.
The target was 100 kilowatts of power.
66.5. We knew that the tidal conditions were really good, so it was tempting also to have a go at really optimizing and driving the electricity production to the peak levels of the system. So we actually run the system beyond the 100 kilowatts it's rated for.
To everyone's excitement, the kite reached 101 kilowatts. Then continued rising up to 117.
The atmosphere in the control room went from a really tense and concentrated environment into really relief and joy and people being really, really happy and proud about what we'd achieved.
Monesto's prototype only generates a fraction of what larger turbines can produce. But they plan to build a machine 10 times more powerful, which would thrust them into the big league.
Around the world, there are thousands of potential installation sites. All continents and all oceans have an abundance of kinetic energy of the kind that we can use. And we talk about a capacity long-term that will be in the range of what nuclear is providing to Earth today. So it's not just sort of a niche technology in that sense. It's something that will play a global role in contributing to getting us where we need to be as humans.
If Monesto successfully scale up their kites, this technology could hold huge potential for the future. In the meantime, others are rapidly proving that tidal stream energy could make a big splash even sooner, with full-scale turbines ready to go. Atlantis have started deploying their turbines around the world.
We are busily planning our first project in France. We've just sent a turbine to Japan. It's a first of its kind in Japan, and we also designed and helped install the first 500 kilowatt turbine in China earlier this year. You've got so much potential around the world for the deployment of this, we're never going to be short of customers.
Sustainable Marine are busy conquering the Bay of Fundy in Canada. If their platform works there, it'll work anywhere.
I think where our technology can really make a difference is in these remote island and coastal communities where perhaps they don't have the best solar resource, perhaps they don't have the best wind resource, but we can give them a renewable and predictable source of power.
And Orbital are putting finishing touches to the biggest and most powerful tidal stream turbine the world has ever seen.
The challenge of climate change doesn't need just one solution. It needs lots and lots of different solutions. So we really want to exploit this pioneering, enabling bit of technology that we've developed here to see it used as widely as possible around the world to generate clean, sustainable power.
A new golden age of ocean power could be around the corner.
100 years or so ago, tidal energy was really pushed out by fossil fuels because they were cheaper. But we've now seen the problems we're having with fossil fuels and the impact it's having on the planet. So I really see that tidal energy is on its way back. And frankly, I think tidal energy is going to get its revenge for being pushed out.
When it comes to energy, could the tide finally be turning?